Alright, in this video we're going to be talking about pathfinding algorithms, and before we get started I'm just going to go over some of the places that we are using pathfinding algorithms, where those algorithms have to be coded into modern electronics and software. So first, and possibly the most obvious, would be video games. If you've played an RTS or you play a top-down MOBA or something like League of Legends, you click on the mini map and you hope your character goes from wherever he is to wherever you clicked. And in order to do that, it has to have a path. And so the pathfinding algorithms are going to be used to find a path from A to B, navigate around whatever obstacles are in the way, and hopefully find the shortest path or the quickest path. And so that's what we're going to be looking at. Other places we see pathfinding algorithms are in general AI, in our GPS and mapping systems. Also, we see a lot of this in robotics. If you've got a Roomba vacuum cleaner or you have a Tesla car or something like that, all of those use pathfinding algorithms. And also in networking. So if you're establishing a connection from, let's say, one server to another, and it has to go through several different points in the internet to make that connection, you are going to use some sort of pathfinding algorithm to find the shortest path or the quickest path or the path of least resistance so that you can establish the best connection. Before we get into the actual pathfinding, we're going to look at how the data is laid out for places you could be and the viable paths that can be taken from one place to another. And this is typically done with a graph, and that's what you see on the screen right here. The graph can be in the form of a grid. It can also be in the form of just random places with random connections from certain places to others. And so this is a random graph right here, and this is like a grid graph. With a grid, we're going to assume there's a connection from every block to any adjacent block. And depending on your algorithm, you may want to include the diagonals, or you may want to only consider horizontal and vertical connections. Each one of these places you can be on a graph is called a node, and the connection from one node to another is called an edge. And so here on this graph, I have all of these different nodes, and I have them all labeled as something different, and each black line represents a viable path from one node to the next. So from F to M is a viable path, but from F to Y is not. You would either have to go from F to E and then to C and then to Y, or from F to M to 7 and then to Y. So that's what the edge indicates. And the algorithm I'm going to be discussing and the algorithm we're going to be coding is called the breadth first search. And it is an algorithm that starts at one point and it starts looking for another point, and it spreads out from wherever you start in all directions looking for whatever that target point is. So this green square is my starting point, and I'm going to make a red square here. That is going to be my target point. That's where I want to get to. And so the way the algorithm works, it starts off at the starting point and it looks at the adjacent nodes. For this example, I'm only going to consider the horizontal and the vertical nodes as connections. And the way the algorithm works, it starts at the starting point and it looks at all adjacent nodes. I'm going to change colors here. So these are the nodes that can be reached from the starting node. And from there, it's going to choose one of these nodes and look at all of the adjacent nodes to it. And so I'll change colors again. And let's say we're starting here now. We would look at this node, this node, and this node. And then it would move to the next node it found, and it would look at the adjacent nodes there. And it would move to this one, and then this one. So this is how our path, our search, is expanding out from the center. And it continues that that algorithm. And so the pattern it forms is said to look like spilled milk. It just spreads out from the middle in all directions. There's nothing indicating to the computer that it needs to be going in this direction. There are other algorithms that do take that into account, such as the A-star algorithm, but they are a little more complicated than the breadth first search, so we won't bother with that right now. In most cases, the breadth first search is going to be good enough, especially if you're working over a small graph. If you have a really large graph, let's say you had 1 million nodes or something like that, you would probably want an A-star algorithm. It would be much more efficient than using a breadth first search. And once it is spread out this far, it is finally going to reach the target node. Now it's going to need a way of determining the path to take back to the starting point. And so I'm going to show you that here with a different example. All right, so in this example, I've got a little map here, and what you would do if you were doing a pathfinding algorithm on something like this, you would either need to overlay it with a grid, or you need to set up nodes at every stopping point, every dead end, every intersection, and every turning point in the map. And so I've done that, and it's going to look something like that. And I've given every node a different name, just so it's easier to keep track of them. And then you would set up your paths by drawing edges between the nodes that are connected. So that looks something like this. And so the black lines are viable paths between the nodes. And I've got U set up as the starting node or the root node, and I have T in red. That is going to be our target, or the node we are trying to find. And to do this, you're going to need a queue, and a queue is basically a line, like at the bank or at the post office. It's a line where people come in on one side and leave the other. In this case, nodes are going to be added on one end and removed from the other. So I'll set up a queue here, and then we'll start by adding our root node to the queue. So our root node is U. We put that on the queue. We take the first node on the queue, which is only U right now, and we mark it as visited by someone. Now U is our root, so we're just going to say this is the root. And we look at the nodes that are attached to our current node. So we discover 5 and we discover D, and we're going to add those to the queue. So 5 and D. Now when we discover a new node, we mark that node as visited by whatever the current node is. So 5 was discovered by U, or visited by U, and D was discovered by U. And now we are done with U, so we're going to remove it from the queue, and we're going to move to the next one, which is 5. So 5 will discover V, so we're going to mark V, and 5 will discover 4, and we mark 4. And technically 5 would discover the root, but U has already been marked, and so you have to account for that when you're coding this. If it's already been discovered or marked by somebody, you're not going to add that one to the queue. All right, moving on. We're done with 5, so, or I forgot to add, I need to add V and 4. V and 4 are added to the queue. And now we are done with 5, so I will take it off the queue, and we move on to D. D is going to discover P, and D is going to discover H. So we'll add those to the queue, P and H. Now we're done with D. D comes off the queue, and we just continue this process until we find the target node. V is going to discover no one, so it comes off immediately. 4 is going to discover E and 3. And then when we get to 3, 3 is going to discover 1. And it's also going to discover our target. And at the point it discovers the target, we're no longer concerned with the queue. We have what we're looking for, and we have a way of getting back. So target was discovered by 3, so this is going to be our path in reverse order. 3, and then 3 was discovered by 4. 4 was discovered by 5. 5 by U, and U is our route. So this is our path from the route to the target. It's in reverse order, so you have to flip it. When you're coding this, if you use a deck, you can just push front instead of adding to the back, and then you have your path in the correct order. All right, so either way, you're just going to follow this path, starting at the root and making your way to the target. So from the root, we go U to 5, 5 to 4, 4 to 3, and 3 to T. On this map, the nodes are spaced differently, so it's not necessarily the shortest path, but it is the path of least resistance, or the shortest number of nodes you could encounter in getting from the root to the target.